Yes, now we return to our original example regarding the purchase of stocks and can now use what we have learned to solve the task. What was the whole thing again? The setup was as follows. We have two random variables, x and x, which are independent and represent the returns of two stocks. And independent means in this context that, yes, these stocks have nothing to do with each other. I might want to mention right away that this is, of course, a rather unrealistic premise, as all stocks are somehow connected to global economic events. Of course, there are stocks, perhaps in different countries and different industries, that are more independent of each other. Yes, but we need this premise because it allows us to calculate much more easily. We will see that shortly. We know the following. There are two expected values, namely 1 and 2, and they are identical. This means that, on average, both stocks reflect the same returns. This means it doesn't matter whether I invest in stock 1 or stock 2, on average, it will yield the same return. But, and this is the difference between these two stocks, they have different risk levels, which can be indicated by the variance that the two random variables have. And we assume that stock 1, that is the return, has a variance of 1. And for stock 2, it has a variance of 2. What does that mean? This indeed means that the risk in stock 1 is smaller than that of stock 2. Yes, okay, so these are our situations. And the question now is, we have an amount that let's say, or we have a ratio and we want to invest a certain percentage in stock 1 and a certain percentage in stock 2. And the question is, what percentage or what share alpha in the range of 0 to 1, how much should I invest in stock 1 and correspondingly 1 minus alpha in stock 2 in order to maximize my return while minimizing my risk, which is essentially my variance. Okay? And that's exactly what we want to calculate now, and for that, we need everything we have learned so far. We ask the question again, and what we will see do first is to consider the following composite random variable, which is alpha times x. That is the return of stock x when I invest alpha, plus 1 minus alpha times x, which is the return I get when I invest 1 minus alpha in stock 2. And combined, this is my total return. And we remember we want to find alpha, so that the expected value of this random variable is as large as possible, while also keeping the variance as small as possible. Let's first consider the expected value, which is relatively simple. We have the following situation. We can form the expected value of this sum here, and we already know that it is linear. So the expected value of x, y, is the expected value of x plus the expected value of y, and we can also simply factor out constants. So we have alpha times ex. And ex and ex are identical, meaning we have alpha times 1, alpha times. And what does that result in? This means that regardless of how we choose the ratio between stock 1 and stock 2, the expected value remains the same. This essentially means that we cannot change our expected return by altering the ratio. That is the answer to question 1. So how can we maximize our return or our expected return? Well, not at all. We actually can't change anything there. But that's also good. It means we still have all the options and can now consider how to minimize the variance of the whole. And for that, we use the same idea. We write down the variances and take a look at them. So on one hand, we write down the variances. And then we have learned that we have a term 2001, which gives us the sum of the variances. We will have this here, and thus we get this covariance term. Okay, so on one hand, we separate the sum and then we still get the variance. We can factor out getting our alpha squared and 1 minus alpha squared, and then we get this 2 times covariance term, where we can also factor out the alpha and 1 minus alpha. With the covariance, we haven't quite seen the calculation rule like that, but you can relatively easily understand that you can also factor out terms there. So now we are in the situation, and now we use this. We use for the first time that we know that x and x are independent, which means that this factor here disappears. 2001. This is good because it means that our variance looks as follows. So we can simply write the variance here as alpha squared variance x plus 1, alpha squared variance x, and variance x is 2, and variance x was 1. So in the end, we are at this term here, alpha squared plus 2 times 1 alpha squared. And now let's remember the question. We want to find an alpha such that the variance is as small as possible. So we want to find an alpha that minimizes this term here, and we can take a look at that. So let's see what it actually looks like. We will write down the function. It looks like this. And this is a parabola that opens upwards. This means we need to find the vertex of this parabola. And we can do that. We have also expanded it again. This is 3 alpha squared minus 4 alpha squared. And perhaps you remember how to find the vertex again. One way would be to determine the derivative of the whole thing, which is 6 alpha 4. Set it equal to 0, and then find out that alpha equals 4, 6, or 2/3. And that is also the solution. This means buying 2/3 of stock 1 and 1, 1/3 of stock 2. And you can also think for yourself about what happens if we have more stocks, and what happens if they have a different variance spectrum, but we have solved the task. Yes, what should you take away from this entire video series? You should take away that we have expected values, variances. You should know what calculation rules exist for these. You should be able to calculate these in simple cases, and above all, pay attention to which calculation rules actually apply in which situations. So which laws apply when we have independent random variables, and which laws apply when we do not necessarily have independent random variables. Yes, in the next chapter we will deal with individual distributions, especially the normal distribution. Until then, take care.